In this video, we're going to look at the compressibility of a van der Waals gas. And by compressibility, I'm talking about the compression factor. So we looked at this in a previous video, where the compression factor is just a ratio between the molar volume of a real gas and the molar volume of the ideal gas, right? So when you have a state equation that's supposed to define your real gas, you can actually quantify how much it deviates from ideal behavior by actually calculating this compression factor for your gas. Now, before we get into this calculation, I want to re-express both the ideal gas law and the van der Waals gas in terms of molar volume, right? So molar volume, in case you guys aren't familiar, so molar volume is basically just the intrinsic property of volume, right? So, whoops, let me use V bar instead of V here. So our molar volume is V bar, right? And it's just equal to the total volume divided by the number of moles, right? So, just like you have, molar mass, which is the mass per mole. Same thing here with the volume. We have a molar volume, our distribution of volume per amount of our substance we actually have. So what we can do is rewrite the rewrite the ideal gas law and the van der Waals equation in terms of molar volume. So we know that the ideal gas volume is going to be V equals nRT, right? So to rewrite this in terms of molar volume, all we have to do is just divide both sides by N. And if we do that, then we end up with V bar is equal to RT over P. Yep, and that should be pressure here. Right, so RT over P. Right, so that gives us our molar volume in the ideal case, right, just by dividing both sides by N. And the same thing with the van der Waals equation, right? So if we go to the van der Waals equation, pressure is going to be equal to nRT over V minus NB minus A N squared over V squared. Right, so basically, in order to get this in the form of the molar volume, right, all we would do is just substitute in V over N instead of volume, right? So then our pressure in terms of molar volume becomes nRT. Oh, wait, no, not N. So it's basically going to get rid of all of your number of moles statements there, so or variables. So RT over V bar minus B minus A over V bar squared, right? So in this case, you just end up with your molar volume rather than your total volume. Okay, cool. So now we're actually ready to use this, right? This information here that we have our molar volume, ideal and van der Waals gases, to derive the compression factor. So let's do it. So first off, when we're talking about the molar volume here, this is the ideal case, so I'm going to put V naught there, right? We can go ahead and plug that into our expression for the compression factor, right? So we can say that Z is equal to V bar over, and then plug that guy in. We'll have RT over P, right? And then making this a little bit cleaner, that'll give us P V bar over RT. Right, so if we want to get the compression factor for the van der Waals gas, all we have to do is take this pressure equation, right, that we already have here for the van der Waals equation, right? We just take this pressure, multiply by V bar, and divide by RT, and that gives us our compression factor. So let's do it. So first, if we multiply by V bar, right, then we're going to end up with RT V bar here over V bar minus B minus A over V bar, right? So one of those V bars is going to cancel out when you multiply the whole expression by V bar. Now all we do is just divide by RT, and that gives us our compression factor, right? So we have PV bar over RT. Then that's going to give us in this term V bar over V bar minus B minus A over RT V bar. Right? So this is the compression factor for van der Waals gas. Right? Now, it may not look like much, but let's sit and analyze this for a second to see what this is telling us, right? Keep in mind that the compression factor is how much a gas deviates from ideal behavior. So if you want to interpret an equation like this, what you're really asking yourself is, under what conditions is this equal to 1, right? And so what this is telling, if we look at this first term, right, this can easily be equal to 1 if the excluded volume is very small, right? So if the excluded volume is roughly equal to the real molar volume, right? So we looked at that case in the van der Waals expression, the van der Waals example that we looked at last time, right? If you're under the conditions where the excluded volume is not that important, then you'll pretty much be at ideal behavior, right? And then this second term can pretty much be negligible if the volume is large enough, right? So if the volume is large enough in this second term, then this second term more or less goes to 0, right? And then you would just be left with 1 in this first term, right? So that's kind of how you want to be able to interpret these compression factor expressions as, under what conditions would this expression give me 1, which would be roughly ideal behavior.